Hi everyone, I'm Luca. I'm a fourth-year student here with Stefano Discetti and Marco Raiola. So today I'm going to tell you a bit more about my PhD. Does this work? Yes. Okay, so my PhD is about jet flow control. So jet flows are basically everywhere in nature, but especially also in industrial applications. And they're amazing to move momentum, but of course they have some issues, especially when they become turbulence. And you can think about noise. So the typical example is the noise reduction issue that we have in aviation, which is limiting operations of airport and aircraft. You have the optimization of mixing in combustion chambers to reduce the production of pollution and increase the performance of combustion. But also for cooling, which is very interesting for electronic device cooling. Now, my PhD stands in the development of a system to observe and control jet flows, turbulent jet flows. So we can think about the typical control loop of a system, where we have a physical system, in our case, the jet case with a certain dynamic F, where we can evaluate its performance to a cost function we call J. And then we sense what is really going on in the jet with some sensors. We feed the control law, which actuates through some actuators. Now, when you try to apply this to fluid flows, it becomes a bit more complicated because you have a very high-dimensional problem. You have Navier-Stokes, which are highly no-dimensional. And then you have issues also with where you place the sensors, how are you really actuating. So my PhD is basically about the design and implementation of a jet flow facility for control, getting some control solution that we can interpret. And as you will see, it became also the development of some imaging technique for in-the-loop implementation of this sensing technique. Now I'll start quickly going through the physical system. So basically, no facility, no experiment. So we started doing our facility. We wanted to reproduce the free field environment, both from an acoustic point of view. So we had to insulate our room where we were doing experiments, also from the point of view of reverberation, but also, and then from the fluidic point of view, which means no recirculation inside our room. So we kind of built also this kind of secondary room where we have our dissipation of the jet flows. And this was the beginning of the PhD. And this is kind of final results that we got here at our university in the lab. Now, moving quickly also to the part of actuation, we decided to actuate using synthetic jets. Synthetic jets are an amazing device, which are very compact, portable. They allow you to entrain some momentum inside the flow. Basically, it's made by a membrane in a cavity, which is oscillating, and the changing volume inside the cavity is generating a trail of vortices, which is introducing a momentum inside the flow. So we build our own, again, we have in our case loudspeakers that are our membrane, which is oscillating, and you can characterize, and then basically you can build your actuation. You can actuate at different frequency and different velocity, depending on the power and voltage amplitude that you put at your actuators. And this is a kind of final result that we had. We have like 6 of these synthetic jets mounted radially, actuating on the main jet, which is this one at the center. So we are shooting radially. Now, moving to the most interesting part is probably the sensing part. So you are controlling a jet. A jet is typically made of very coherent structures. Coherent structures means like this dominant pattern in your flow that are dominating the dynamics of it. And if you want to trigger, you want to control noise, you want to control mixing, usually what you have to do is to go against this kind of structure or control them. So here you can see on the left a visualization in an experiment. We were exciting specific structures and we were visualizing them with PIV. And these are the kind of, from simulation of main features and coherent structure that you get in a jet. So typically what people do when they do experiments for jets, they put some sensors, for example, this one in the red block, where you can, these are microphones that are sensing the jet, trying to sense exactly these coherent structures, and then you actuate against these. So can we really infer the coherent structures dynamics from these very few sparse probes that we have around? So first thing we did was, okay, let's go to the lab, we do our experiments, we have our jet, we place our probes inside. The probe sees some signal, all right? Then we have also PIV. PIV is amazing. It gives you like a specially resolved measurement of your jet. And so you can see like the proper coherent structures. You can get very interesting results, but it's not time resolved. It means that you have only one of the snapshots every few time instants. In the middle, what can we do? Usually what we do is you try to infer what was going on in the middle from the probes. What you do is what we call the enhanced temporal resolution. So we started doing the experiment. We started with a water jet. We started with some synthetic probes, so they were not real. They were just an extraction of the velocity field in points. And we could see a correlation between the probes and the velocity fields. If you have correlation, you can estimate what is going on in the middle. So this was what we got at the beginning. So in our synthetic case, we could kind of reconcile what was really happening. But then we moved to the lab. We tried to do it really in reality, and of course, it failed miserably. So there was no correlation between our probes and the velocity fields. So the flow field failed. Now, what could we do now? basically, it was the end of my first year. I started going around some conferences telling about my failure. And there I basically had the chance to meet this guy. He's Chris Wheeler from DLR, or an urban legend is probably myself in the future coming back to tell me a solution, who I was discussing with him about why not using velocimetry, imaging velocimetry in the control loop. I mean, the guy is a kind of godfather of PIV, so he kind of gave me a hint. Well, PIV has an issue because, as we said, it is producing a lot of data, and it has a lot of issues because it needs a high-power laser. While probes are amazing, they give you very cheap, they give you time resolution. But of course, PIV will provide you with a much larger observability of your system for your control. Now, the main issue of PIV is that PIV is based on cameras, and cameras are usually frame-based. It means that they suffer of a trade-off between the latency, which is your repetition rate of your cameras, that you want as small as possible in order to have like high-frequency acquisition and high-frequency description of your dynamics. But of course, if you reduce the latency, you increase your repetition rate of your cameras, you increase of the amount of data rate, which gets huge. Now, there's a new technology around, which is event-based cameras, neuromorphic approach, which basically places in this plot, in this point, which is like the wet dreams of every experimentalist. So what is an event-based camera? An event-based camera, this is on the left what would do a conventional frame-based camera. It gives you like frames of what is going on in your scene at a fixed time step. When you talk about event-based camera, it only tells you what is really changing in your scene, what you are observing. So it comes with several advantages that we could leverage to our approach. So basically now you will have a continuous description of your flow, and only what is really changing is what matters to you, and you're observing only that. So the big question that we posed ourselves at the beginning was, is it good enough for our flow application? Can we do it? So we started applying it, comparing conventional cameras to these event-based cameras. So we did an experiment. We were looking at the same flow field, and we tried to describe that kind of main structure that I was telling you at the beginning. And there's also an interesting difference in the price, of course, because high-speed cameras are in the order of 200,000 euros, event-based cameras is 1,000 euros. So this is kind of the dynamics of the main structures. In black, you can see it is what a conventional camera would see, the dynamics of these structures, and in red, what event-based camera could reconstruct, and it was spot on. So we were like, okay, event-based can work for reconstructing this kind of coherent structure that we want to target. And so from that, we moved also to a real-time implementation, meaning that now real-time is a specific word. I would say data-efficient implementation, meaning that you can go at a very high frequency in processing this kind of data from imaging. So we also developed a way to have from a very low resolution real-time measurement, this one on top, a high resolution estimation of what the flow is really doing, all of this in real time up to a few hundred hertz. So basically, it allows us to say, okay, we kind of develop a new sensing way to observe the flow at a specific way with a very good observability. So we could now go back to our lab and do the control. So we went back to our jet, and we tried to implement event-based cameras in the control loop. So we did it in two ways. The first one was basically simply replacing the reward estimation with event-based cameras. So now we have the jet, which is actuated, and we are evaluating the reward at the exit of the jet and maximizing what is the turbulent kinetic energy, so the mixing of the jet, depending on what the event-based camera was seeing. A second approach that we did was that now the event-based camera is also providing you not only the reward, but also the state of your system. So we divided what the event-based camera was seeing into two areas, one for state evaluation and one for the reward of your control. Now, going quickly through the results, we have that both kind of worked in the sense that this is the open loop optimization. So this is the reward that the event-based camera was evaluating and optimizing the control. And you can see here, maybe this is more interesting. On top left, you can see the uncontrolled jet. And the other three cases are three cases of control, where you can see run 8. Oh, sorry. Can I go back? No. OK, yeah. So you can see that increasing the number of tests, we could actually arrive into an optimal condition where you can see that the amount of fluctuations in the flow is much, much higher. And this is what the event-based was pointing to. Now, then we also, for the part of the closed-loop control, here we have an experiment in water. Now, this is also done in collaboration with Politecnico di Torino and DLR. So here, basically, again, you can see here the first part before the actuation is for the state estimation from event-based, and the last part is for the reward estimation. And here we implemented the reinforcement learning, which actually with a sufficiently small number of episodes could again increase the tubular kinetic energy in the reward area. So, concluding, I'm writing in order to finish all of the work that were open and stuff. And actually, since yesterday, I'm part of the proof of concept of Stefano for trying to bring event-based cameras to a higher TRL level for industrial applications. So these are a few contributions, and that's it. Thank you for your attention.